So getting back to here, if you've got two trolleys here, and what I'm saying in this case, and what I do is I put these two together and make a little explosion and move apart, is this one is going to have a large mass, and this one's going to have a small mass, which means then the velocity of this one when it moves away, if this mass is going to be very, very large, its velocity must be small, but in this one, the velocity must be big because the mass is low. Therefore, it does make sense. It goes in the ratios. Now, this is a quite funny video, but this shows you it in action. If I get this little video to work, here we go, and you've got here, instead. Now, pause it. Yeah, pause. Now, here you've got a rifle, and you've got some firing range. Now, in here, you've got this bullet, and the bullet's about to go flying off this way, but beforehand, the momentum must be zero. Well, the momentum must be zero, but afterwards you've got explosion. Therefore, the bullet goes to the right, the gun then goes to the left. But because the bullet has a lot less mass, it goes off with a very, very high velocity. But this is recoil, isn't it? Because the gun goes back in the opposite direction, but because the gun has got a much larger mass, it can move off with much less velocity. Cracking video. It goes so far back it smashes the glass in the screen there. Okay, now we're happy with that. Getting back to my presentation is going to skip that. This is a tricky one. Now, again, what I advise you to do is I would advise you to freeze this now, and can you think of the answers? So this is getting back to what I did right at the beginning, is where the rocket is going up to the right here. Now, we looked at these beforehand, where you have all the gases going down this way here. Therefore, it creates gases going this way, it creates a force in the opposite direction, make the rocket go up to the right in this case here. Okay, this is Newton's laws all in action perfectly. So all the gas is escaping here, and then the rocket goes in the opposite direction. But I need to have conservation of momentum. Therefore, what I've got here is that mass is ejected at delta m over delta t, and this is where you have mass changing with time, and this is where the force and impulse comes in. So you've got delta m at delta t. I'm going to have the gas ejected out with velocity v. Then the rocket's going to the right here, and the velocity of the rocket is going to be a big V, and therefore it's going to have, in a time delta t, the speed is going to increase by delta v, because the rocket is going to get faster and faster and faster. The gases are going to escape at a constant velocity v. So the questions I want you to think about is, the rocket has a mass large m. That's what I missed off here. Is what's the momentum of the gas jet? What's going to be the total momentum of the rocket and the jet? Is this a collision or explosion? What can you say about the momentum change of the rocket and the gas jets? How can you show this mathematically? And can you calculate the thrust of the rocket in terms of symbols? And then finally, number 6, what is the momentum change of the rocket? So freeze the video, jot down some answers, start the video again, and I'll give them to you. So here they are. Okay, now here's your rocket. Now, as I mentioned before, these are going to be ejected at delta m, and it's going to happen in delta t. Okay? Therefore, doesn't it make sense? Momentum is going to be mass multiplied by velocity. Well, the change in momentum, which is going to be delta p, is dead easy. Isn't that going to be your v, because they're going out velocity v, multiplied by the change in mass, i.e. the mass ejected in time t, in delta t, sorry. Okay? Therefore, when we look at the other way, here we've got a minus delta p, and now this is all to do with the rocket. Now it's a negative because it's going in the opposite direction. So saying that is going to be negative, and this direction is going to be positive. Okay, now the minus delta p here, okay, is going to be the big mass of the rocket multiplied by the change in velocity at m delta v. Therefore, and this little bit of mass in here, it says momentum before this explosion, because it's going to be an explosion, must be 0. The rocket was sitting on the ground. Then the explosion happens and all the gases come out here. The momentum afterwards still must be 0. Therefore, doesn't it make sense for the fact, it depends which way you take it, the two changes in momentum must be equal to each other. Okay? And actually change this. Notice it. Let's call that now minus delta P going that way, and that's making that positive. Doesn't make any difference, but one going one way and one going the other way, but they must be equal. They have to be, because the total momentum must be 0. That is why they come up with the equation just here of the mass multiplied by delta V, and that's going to be for the rocket, must be then equal to the negative of the V multiplied by delta M. That's going to be the momentum of the gases being taken away. And what they've got here is just got the, well, they call that here minus, and they call it a plus, and they're swapped over. It doesn't make a difference, the negative each one. That means then what they've done here is to work out the change velocity of the rocket, okay, which is delta V. You've got your minus V delta M, and all you do is you divide it by your M, because you take the M down here, and that is where that equation has come from. Okay? Well, to work out the thrust of the rocket, and I'm going to stick this over here, you know the force is going to be changed in momentum, which is delta P over T. So it really doesn't matter which one you take, because the two must be the same, because the force on the rocket must be the same as the force of the gases going down, because that is Newton's third law, isn't it? That's why then you've got your M multiplied by your delta V divided by delta T in that one there, or you can have here minus V delta M divided by your delta T, because this one is going to be the one for the rocket, and that's going to be the gases coming out. Okay? And what I've just been through is the questions in the previous slide, just over here. Now, what I'd like you to do, and I'm going to make a second part of this video next, is I'd like you to go back to this. I want to see if you can answer the questions. Tick the right boxes here. If you're listening to the video beforehand, going through, it's exactly the same as the rocket, you should be able to do it. Right, sign.